Yes, Professor. Now we have started streaming. You
Okay,
may please
thank you.
start. Okay, okay.
Okay. Uh, so I think last class you had done some problems. Um, so Shitikanta, can you just tell me what problems did you do?
Yes, sir. Sir, I started with that simple problem. One problem from classical mechanics I have
Ah,
solved, that time period and amplitude relation for a power law potential.
okay,
Yes, sir. Then I solved this problem. Simple
mm,
pendulum and harmonic oscillator.
okay,
I have just introduced that what is the gauge invariance for Lagrangian.
okay, okay,
That's it.
okay. Very good. Uh, so so I hope you have followed what was discussed in these problems. So let us try to do. Mm, let's try to get some more experience of partly a part of this lecture. I will try to spend some time on some problems, and then a part of it I will try to elucidate some concepts. Okay, so what is that we want is that we have uh, so we have this Lagrangian. So you have to set up a Lagrangian, and Lagrangian is the kinetic energy minus the potential energy. This is what we understood. And then once you have a set of generalized coordinates, let's say q1, q2, etc., qn, and this n is the degrees of freedom, n is the number of degrees of freedom. Okay, and if you have this, then you have this Lagrangian, which is a function of q1 to qn and q1 dot to qn dot, and could be a function of time. And then you have what are called Euler-Lagrange equations of motion, which we have derived on the other day. So dou L by dou Qj minus d by dt of dou L by dou Qj dot is equal to 0. So these are equations of motion. These are called Euler-Lagrange equations of motion. And you actually solve this for all j. For each j, I mean for each qj, you will have one equation of motion. So there will be n equations of motion in total for an n degree of freedom problem. Okay, so you have solved the problem of a pendulum last class, and you have understood what is the generalized coordinate, what is the equation of motion, how to solve it. Okay, so in most cases, what happens is solving this equation of motion becomes uh, difficult, because most of these equations of motion turns out to be non-linear differential equations, and there are no general methods to solve nonlinear differential equation. As a result, solving those equations become difficult. But we can always set up the differential equation, and then if you are interested in solving, you can always solve it on a computer. So you can solve it numerically. Okay, you get some idea about that. That's an approximate solution, but you get some idea about the solution. Okay, so maybe I will first discuss one problem which is of large interest, and usually mechanics started with this problem. So namely, this problem is that of a central force problem. Okay, so one of the examples that I would like to talk about is central force problem. Okay, so generally we are interested in a problem like this. Suppose I have a mass m1 here and another mass m2 here. Okay, so let's say you have some coordinate system, and let's say this has got a position vector r1, and this has got a position vector r2, and this vector is a relative vector, which is r1 minus r2, which I will call it as r. Okay, so now this is basically what is called a two-body problem. Okay, I'm not going to show you, but I'm going to state that this two-body problem can always be reduced to an effective one-body problem. Okay, so when I reduce this to an effective one-body problem, what I have is that I have what is called a force center, and then this is a geometric point which I can consider as origin of my coordinate system, and then I have a mass. This is a single body at a position vector which is same as the relative vector here, and the mass here is basically a reduced mass, so which is equal to m1 m2 divided by m1 plus m2. Okay, so a two body problem can always be reduced to, so this is a two body problem and this is a one body problem. So in other words, an effective one body problem.
Sir, R vector in both cases, both two body problem and one body problem is the same, the relative distance, sir. So,
They are same, relative distances.
okay.
So that means the force center is actually kept at this mass, and then this mass becomes the reduced mass. That's what it means.
Okay, sir. So what is exactly force center, sir?
Basically, this is the point towards which or away from which the force is acting. That's what it means.
Yes, sir. Thank you, sir.
Okay. Now there is a force. Um, so the force F can depends on R. Okay. So this is in general. Uh, so when you reduce a two body problem to one body problem, your force can be like this. Okay. But if you have a situation that this force has a particular form, in the sense this is only a function of the magnitude r and is directed along r cap. Okay, so if this force is equal to this, then it is called a central force. It is called a central force. Okay, so what does that mean? That means that the force depends only on the distance from the force center, or if you are talking about two body problem, it depends only on the distance between the two bodies, and the force is also directed along the line joining these two objects. Okay, like gravitational force, or the what is that Coulomb force. So these kind of forces are central forces, and that is the point that we are trying to understand. So we will be trying to understand motion under central force. So that means we are assuming that the force depends. So in spherical polar coordinates, for example, this vector r can be considered as r theta phi, correct? In spherical polar coordinates. So that means the force is independent of theta and phi. Okay, force here is independent of theta and phi.
Professor, your voice is very less.
Oh, okay.
Mm.
So force
Yes.
is independent of theta and phi. That's what is basically central force is. Okay, so central force where the force is independent of theta and phi. So that's what is the central force. I mean, that is the definition of central force. Now there are certain general observations that we can make. So one of the observation that we can make is, if you ask a question, what is the torque? What is the torque acting on the mass, on the body? Okay, if you ask that question, and usually torque, which some people denote it by N, or some books will denote it as tau. So N is equal to, by definition, it is R cross F. That is the definition of torque. But for a central force, you can notice that this N is equal to R cross. So this F is basically some F of R into R cap. Okay. Now R vector cross R cap is 0 because they both are in the same direction. So this is a 0 vector. That means there exists no torque. Okay. There exists no torque. Now this implies we have that rate of change of angular momentum is equal to the applied torque. This is like Newton's second law for angular motion. Okay, so dl by dt is equal to n, where L is the angular momentum. And for central force motion, we find that the angular dl by dt is equal to 0. What does that mean? This implies this L vector is constant. Constant in time. That's what it means. Okay. Or we say that angular momentum is conserved. Angular momentum is conserved. For central force. Central force motion. So this immediately has one very important consequence. See, L is constant, means it is a constant vector. Okay, so when I say L vector is constant, its direction is also constant, its magnitude is also constant. Now, direction of L is constant in time, constant in t. That implies we have L by definition is R cross P, because R cross P is L, right? And so direction of L is perpendicular to the plane containing R and P. That is the meaning of cross product. If R cross P is always perpendicular to the plane containing R and P. Now read these two sentences together. Direction of L is constant in time. Direction of L is perpendicular to plane containing R and P. These two sentences mean that, okay, so this means that R and P always lie in a plane, and that plane is fixed. It will not change with time. What does that mean? R is the position, P is the momentum, and if they don't change that plane, that means the motion under central force is two-dimensional. Okay, so this implies motion under central force is two-dimensional. It will always be in some plane, two-dimensional. Okay, so that means we require two generalized coordinates. Okay, so we need two generalized coordinates. Okay, now, so if you say you have a plane and two generalized coordinates, you can call that as xy plane and take the coordinates are x and y. But we can choose more intelligently. How? Because let us say that I have my force f of r. Okay, this force can be obtained from a potential, let's say. That means if it is possible to obtain this force from a potential, if this of course this is in the r cap direction. Okay, so if I can obtain this from a potential v depends only on r. V depends only on r. Okay, so we call this as central potential. Okay, for example, uh, if you have a force which is equal to minus k divided by r square into r cap, then implies this potential is going to be equal to minus k by r. Okay, potential is a scalar quantity and force is a vector quantity, but you can obtain this from a negative gradient of this potential. So this is called a central potential. Now potential depends only on r. So it is always better to choose generalized coordinates as polar coordinates. That is, you choose r and theta, so that the potential depends only on one of them. Okay, so it is convenient or a better choice. Okay, so the generalized coordinates
Sir, potential should be plus k by r, no, sir?
no, if you take there is a minus sign here, no?
Yes, yes, sir. Yes, I got it.
Uh, so generalized coordinates, I'm going to choose them as r and theta. Okay, so now it is simple. You can write down your if you want to write down your Cartesian coordinates, so you can write x is equal to, so you imagine that you have got a plane and this is x-axis and this is y-axis and this is kind of a distance r and this is theta. So this r and theta I'm choosing as generalized coordinates. So you have r cos theta and y is equal to r sin theta. So I am expressing these polar coordinates or Cartesian coordinates in terms of these generalized coordinates. So this is a 2 degree of freedom problem. So degrees of freedom is equal to 2. Okay, now we can write down our kinetic energy. Kinetic energy is equal to half. I'm calling this as reduced mass into x dot square plus y dot square. Okay, which is so you can write down x dot from here as r dot cos theta minus r sin theta into theta dot, and y dot is r dot sin theta plus r cos theta into theta dot, and you square it and add it, then you will get half mu r dot square plus r square theta dot square. The cross terms will cancel and you have this as your kinetic energy. Now the potential energy, I will not consider any particular form of the potential energy for the moment. So the Lagrangian for a central force problem. Okay, so let us let V of R be a central potential. Okay, then the Lagrangian for the central potential problem will be, so the Lagrangian L, okay, will be equal to half mu r dot square plus r square theta dot square minus V of R. So right now I'm going to keep this V of R as V of R itself. Okay, so now there are 2 degrees of freedom. So we have to write down Euler-Lagrange equation corresponding to 2 degrees of freedom separately. Now let us try to note that in this Lagrangian, okay, so note that the Lagrangian is independent of theta. Independent of theta. What does that mean? That implies the partial derivative of L with respect to theta is equal to 0. Okay, so if you consider Euler-Lagrange equation, Euler-Lagrange equation for theta, if you consider Euler-Lagrange equation for theta, so you have partial derivative of L with respect to theta minus dl ddt of partial derivative L with respect to theta dot is equal to 0. But since L doesn't depend on theta, this itself is equal to 0. So because of that, what happens? So this is 0. So that implies d by dt of del L by del theta dot is equal to 0. What does it mean? That implies dou L by dou theta dot is a constant of motion. That means that factor does not change with time. It's a constant of motion. Okay. So this is a general general way in which one can find constants of motion. So there is a general thing that if Lagrangian does not explicitly depend on some generalized coordinate, say some q or some q. So maybe we can call that particular coordinate on which it doesn't depend as some q tilde. Okay. Then q tilde is called cyclic coordinate or ignorable coordinate. So if you can identify cyclic coordinates, okay, then the corresponding canonical momentum, okay, so the canonical conjugate momentum, which I will call it as P tilde, which is defined as
Sir, what is that? Sir, excuse me.
Yeah.
Sir, what is that canonical conjugate momentum, sir?
That is what I am defining. If you say you have a Lagrangian, and then dou L by dou Q dot is called the canonically conjugate momentum. Okay.
Okay, sir.
This is how we define a canonically conjugate momentum.
Means, is there something meaning for that word canonical conjugate moment?
See, conjugate means it is like Q tilde is pair of P tilde, like that. Okay. Conjugate is always corresponding, right? So canonical is a general word that is used here. I think the English meaning of canonical is it is conventional. Okay. So that is the kind of a link, and we will see later that sometimes this canonical momentum is not same as the momentum that we know, which we call as kinetic momentum. So kinetic momentum and canonical momentum are not same in general. In many cases they turn out to be the same, but not always.
Okay, sir.
Okay, but canonical conjugate momentum is always defined like this through Lagrangian.
Okay.
Okay, so the canonical conjugate momentum corresponding.
Sir,
Yeah.
You said this canonical momentum and this mechanical kinetic momentum are not this with respect to charge particle kind of thing in a magnetic field.
Yeah. That,
with that
correct,
example,
correct.
sir. Okay.
Yeah.
Okay. Thank you.
Corresponding to a cyclic coordinate. Cyclic coordinate is a constant of motion. Okay, corresponding to a cyclic coordinate is a constant of motion. Now, this is an important thing, and we will come back to this maybe a little later. But at this moment, I want to use this fact. So that means, since theta is a cyclic coordinate, Lagrangian does not depend on theta. then the partial derivative of Lagrangian with the theta dot will become a constant of motion. Okay, so now let's try to so let's look at the Lagrangian. So what is partial derivative, say L with respect to theta dot is equal to mu r square theta dot. Okay, so if you look at the Lagrangian, 2 theta dot square will become 2 theta dot, and 2 cancel, so it is mu r square theta dot. Now this is constant. Okay, so I will call that constant as L. Okay, so this is,
Excuse me, sir.
yes.
So why is the canonical conjugate momentum defined like this? And what is its significance?
See, you will see this has got a relevance in terms of see, correspondingly, if you want to write down a momentum for every particle and then later convert that into a Hamiltonian and so on, so this momentum is what you have to use. Okay, see, it is like this. Okay, let me just complete this. So this is basically a constant. I'll come back to your question. So constant, and then it turns out that this is the magnitude of the angular momentum. That is why I have used this symbol L. Okay, this is constant and it is basically the magnitude of the angular momentum. Okay, so this is constant. This L is constant of motion. Okay, so if you go back, I said L vector is constant. So direction is constant and angular magnitude is also constant. So the magnitude is given by this. Okay, so okay, so now let me just come to this question that you're asking. Suppose you take single particle in one dimension. Okay, so take the example of a single particle in one dimension. Okay, so then what will be your Lagrangian? Lagrangian is equal to half mx dot square minus, let's say, some potential, which I will right now call it as V of x. Okay, now suppose if I ask a question, what is Lagrange's equation of motion? So del L del x is given as minus del V del x. Okay, and del L del x dot is given by mx dot. Okay, but what is mx dot? Mx dot is p, mass times velocity. Okay, and then what is d by dt of del L del x dot? That is equal to p dot. And what is minus dou v by dou x? Is the force. So the Lagrange's equation of motion, that is del L del x minus d dt of del L del x dot is equal to 0. So this is equal to force minus p dot is equal to 0. Or in other words, force is equal to p dot. This is Newton's equation of motion, right? Okay, so from this simple example, I am able to show that this del L by del x dot is equal to the momentum. Now we may ask, okay, fine. So why don't we simply call it as momentum? But sometimes your generalized coordinate, so it is not always called momentum. because your generalized coordinate need not have always the length dimension. Correct? For example, if you take the Lagrangian of a simple pendulum or a pendulum, okay, so for let's say planar pendulum, I guess last time you have done this problem. So for a planar pendulum, your L is given by half ml square theta dot square, okay, minus mg into 1 minus cos theta. So this is your equation of, I mean, the Lagrangian. Okay, so this is you have a pendulum like this, and this is L, and this is theta. So if you have this kind of a problem, so this is the Lagrangian. Now what will be del L by del theta dot? Del L by del theta dot is basically ml square theta dot. Okay, ml square theta dot. So this is not actually the momentum, but this is angular momentum. So whenever you have angle degree of freedom for the generalized coordinate, then the momentum is an angular momentum. When you have length dimension degree of freedom for generalized coordinate, then this is going to be momentum. So like that, there is a corresponding momentum. So I will call this in general a p theta, just to say that it is a generalized coordinate associated with theta. Okay, so this particular quantity, whatever, so for a given q, a generalized coordinate, del L by del Q dot, del L by del Q dot. Okay, so you call this as canonical momentum, or you can call it as canonically or conjugate momentum. Canonical momentum of Q, conjugate momentum of Q, also called generalized momentum. Corresponding to Q. Okay, so this is something which these are some names. Sometimes one name is used, or sometimes canonically conjugate or canonical momentum, like that it is used. So the reason why we call this canonical momentum is, for all generalized coordinates, it is not just the momentum with the same dimension of the momentum. Sometimes it can be angular momentum, or if you have some other exotic dimension for the generalized coordinate, then it may have a different dimension for this momentum. So there is no restriction, so it is generalized. And canonical is always conjugate is always referred to that it pairs with something. So it always pairs with Q. So if you have Q, then dou L by dou Q dot will give you this, like that. So that is how the name is. Is that clear? So this is just an answer to the question, and let's go back. So this,
Sir.
Yeah.
Sir, can you scroll up? Enough, sir. Enough. That is said that L doesn't depend on some generalized coordinate, but it is supposed to depend on a generalized coordinate, right?
Yeah, but it is not necessary that it should depend on all generalized coordinates. Okay, so sometimes some generalized coordinates may not appear in the Lagrangian. So those are the ones that are useful for us in identifying constants of motion. It is not necessary that Lagrangian should be containing all generalized coordinates. There is no such requirement, right? See, when we say Lagrangian depends on generalized coordinates, that's a very general statement. It may depend on some and it may not depend on some. Like the central force problem, we have seen it depends on R. So in general, here we would have written that so L depends on R dot, theta, theta dot. That is what we would have written in general. But it turns out that, but here, this L depends only on R dot, and theta dot. It does not depend on theta. So that is how we identify that theta is cyclic.
Sir, out is not depend does not depend on theta.
I mean, what do you mean by how? We have seen, we have written down the Lagrangian, we have seen that it doesn't depend on theta.
I mean, the potential.
Okay, so the point is, so probably you are asking a question why it doesn't depend on theta. Okay, so that question is interesting. So that question is because, see, if you say that so let's say that you have a force center here, this is your center, and let's say this is your R. Okay, now you think of a circle whose radius is R. Now different points on this circle will have same R value but different theta values, correct? But your force doesn't differentiate between these two. Any point has the same force because your force depends only on the distance. It does not depend on the direction. So what happens, your force is same for all the points on this circle. Okay, in other words, if you have such a kind of force, or if you have such kind of a potential, then you can see that you rotate, let's say that you have body at some position. Let's say the body is here at this point, and then let's say you take from here to here. There is no physically, there is no change in the force. So that means all these positions are invariant with respect to dynamics. So wherever you are not going to get any experience any different force. So this kind of an invariance, or this kind of a symmetry, in this case what we have is a rotational symmetry. So since it doesn't depend on theta, now theta can be transformed to anything else, theta plus some constant. The Lagrangian is same, right? So since we are making such transformation, there is an invariance, a rotational invariance. So the answer why it doesn't depend on theta is because in the problem there is a rotational invariance. Rotational invariance. And whenever there are certain symmetries and invariances like this, there is a they appear in such a, I mean, they actually are responsible for certain coordinates to become cyclic. Is that clear?
Yes.
Sir, there's a question from YouTube, sir. Mukesh Kumar is asking, sir, is there any difference between canonical momentum and normal momentum? And also tell sir for force.
What is the last question?
He's written, and also tell sir for force.
Tell?
I mean, he's addressing you and saying, and also tell for force.
For force?
Yes, sir.
Okay. So, yeah, there is a difference. That's why we are having two different names. So I have to, so you have to wait till when I do that problem of charged particle in electromagnetic field. then you will understand what is the difference between canonical momentum and what the normal momentum you call, which we call it as a kinetic momentum. Okay, or you can try to read up for yourself. So the difference between canonical momentum and kinetic momentum you will understand when you try to write down the Lagrangian for a charged particle in electromagnetic field. Okay, so this is just, I'm just giving you a clue. If you want, you read up, but we will do that problem later. And that for the force, I mean, probably I understand you mean that generalized force and force. Now the difference between generalized force and force is same as the difference between coordinate and generalized coordinate, because generalized force will not have the dimension of the force. So that is the only difference.
Sir.
Yeah.
Sir, so any symmetry in the problem will always corresponds to a correspond to a generalized coordinate whose change will leave the Lagrangian invariant. Is it correct, or it has to do with generalized velocity also?
That statement is correct, but but what I'm trying to say is that any such symmetry or invariance does not necessarily make it a cyclic. So something is becoming cyclic is kind of a stronger, I mean, obvious invariance. But even if there is even if there is a dependence, there can be an invariance.
Yes, sir. Okay, like some combination of coordinates.
Correct. So you will be able to construct the. So maybe I will try to show you this one. This is what is called Noether's theorem. So you can actually construct a conserved quantity from the invariance property.
Yes. So, sir, invariance not necessarily means a cyclic.
Yes. Cyclic means invariance.
But the converse is true. No,
yeah. Cyclic is invariance, but invariance need not be always cyclic.
Okay.
Okay.
Thank you.
Okay. So now let's go back to this thing. So we are having this equation where mu r square theta dot is equal to L. Okay. So now I will write this from this equation. So let us. So we have mu r square theta dot is equal to L. Now you see that this immediately gives us a very important result. For example, let's say that this is our plane and this is the center, and let's say this is where you have your mu and this is r. Okay, this is r, and let's say this is r at time t. Okay, and then this is moving from here to here, and let's say this is r at t plus delta t, and this this distance or whatever this change is what I call it as some delta theta. Okay, now suppose if I ask a question, what is the area? Okay, so this happened in some, so in time delta t, this has happened in time delta t. This is the area swept. So what is this area swept? This is basically, you can say r is much larger than this distance. Okay, so r is large compared to this r delta theta. So you can approximate this to be some triangle, and then this area, which I will call it as delta A, is equal to half r into r delta theta. Correct? So that is what it is. This is like base and this is like height. height and this two sides are same. That's what I'm assuming, because R is very, very large. There is no difference between this. So that means if I ask what is the aerial velocity, delta A by delta T, and then of course take this limit delta T tending to 0, that will be equal to half R square into delta theta by delta T, and in the limit delta T tending to 0. So this gives you dA by dt is equal to half R square theta dot. Okay, this is what we call as aerial velocity. But you know, R square theta dot is constant because that is L by mu. So this is equal to constant in T. That means the aerial velocity does not change. And you may recognize that this is what is called Kepler's second law. Kepler's second law. And of course, Kepler had written down this law for planetary motion. That means it is for what is called a particular potential, that is 1 by R potential. But then we have not bothered about what is V of R here. So the Kepler second law is actually true for any central force motion. Not only for planetary motion, but any central force motion, it is true. Or in other words, Kepler's second law, that means equal areas are swept in equal intervals of time. So that law is actually same as conservation of angular momentum, because from conservation of angular momentum, you can show that aerial velocity is constant. So this is one very general result for any central force motion. So Kepler's second law is true for any central force motion. Okay, so that is one conclusion that you can draw. And
so here, have we assumed that R is constant, sir? I mean R has not varied much. Have we assumed that, sir?
Yeah, in some short time, and that is reasonable to assume.
Yes,
because we are only talking about infinitesimal time, right? So that is reasonable to assume.
yes, sir.
Okay. So now let us try to. So we will try to write down from here. This implies. Let me say this theta dot is equal to L by mu R square. So let me just keep it like this, and then let's try to write down the Euler-Lagrange equation for the generalized coordinate R. Okay, so we have Lagrangian here. Okay, and then you take dou L by dou R and then dou L by dou R dot. So that is what. So let me rewrite the Lagrangian here. Half mu R dot square plus R square theta dot square minus VFR. So dou L by dou R is equal to mu R theta dot square minus dou V by dou R. And dou L by dou R dot is equal to mu R dot. Then d dt of dou L by dou R dot is equal to mu R double dot. So we have written down this dou L dou R minus dTt of dou L dou R dot is equal to 0. This implies. So here what I will do is that I want to write everything in terms of R. So I will make use of this, let's say use theta dot is equal to L by mu R square. Where? In this equation. Okay. So then what happens? We will have mu R into theta dot L square by mu square R to the power 4. So that will be L square by mu R cube minus dou V by dou R minus mu R double dot is equal to 0. In other words, we can write down this as mu R double dot is equal to minus dou V by dou R plus L square by mu R cube. Okay. But I can also write this because L is constant, mu is constant. So only R is the dependence. So I could have written this as minus del by del R of V of R plus L square by twice mu R square. Okay. So you can verify that this is same as this. L square by twice mu R. So minus 2 divided by R cube. 2 will cancel. There is a minus and outside there is a minus sign. And hence it will become L square by mu R cube. Okay. So note that del by del R of L square by twice mu R square is equal to L square by mu R cube. So this you can verify. So I am going to call this one as minus dou by dou R of some effective potential, V effective of R. Okay, where the effective potential which I will call it as V effective of R is equal to the given potential V of R plus L square divided by twice mu R square. And this term is called centrifugal potential. This term is called the centrifugal potential. So the effective potential is a given potential plus L square by twice mu R square. Now we can ask, so what is that we have? We have mu R double dot. So we have mu R double dot is equal to minus del V of R by del, minus del V effective of R by del R. This is what we have. Now we want to solve this equation. So for that, what we will do is we will try to reduce the second order equation into first order equation. Okay, so that is by obtaining what is called a first integral. So let us, so what do we do is you multiply this equation both sides by R dot. So then I have mu R double dot into R dot is equal to minus dou V effective of R by dou R into R dot. Now I'm going to use the trick. So the left hand side I'm going to write it as d by dt of half mu R dot square. Now when I take this, it is 2 R dot R double dot, 2 will cancel, so I will get this. And right hand side is basically minus d by dt of V effective of R. Okay, so this is, it is V effective of R and R depends on T. So chain rule, if you do, then this is what you will get. So this tells you that if I bring both of these things to left hand side, so d by dt of half mu R dot square plus V effective of R is equal to 0. What does that mean? This is another constant of motion. Okay, so that is half mu R dot square plus V effective of R is a constant of motion. I will call it as E. Is another constant of motion. That means it does not change with time. Or it is E, this is a conserved quantity. Okay. Now this is slightly easy to solve because this is a first order equation. So what I will do is I will write so 2 E minus V, 2 times E minus V. Okay, so I can write down dr by dt can be written as 2 by mu into E minus V effective of R. Okay, so this is a first order differential equation, of course, with the square root, because this is R dot square. So you can solve this first order differential equation by writing this in the following fashion. So let us say that I have dt is equal to dr divided by square root of twice 2 by mu into E minus V effective of R. Okay, so now all that you have to do is this is what we call as solution obtained in the form of a quadrature. Now you have to integrate this, correct? So how do you do this integration? Suppose let us say that you are starting from time t equal to 0. So you say 0 to t some dt prime is equal to some initial condition r0 to some point r dr prime divided by square root of 2 by mu into E minus V effective of r prime. I'm writing this as an r prime because integration variable has to be different from the limits. So that's all. You have to do this integration. Now, whether we can do this integration or not depends on, see, remember your V effective of r prime has two terms. One is given potential V of r and then the centrifugal term. So for some problems of the given potential, maybe this is something which you cannot integrate. But up to this, it is it can be brought. So if you cannot integrate this for any given potential, then you have to again do a numerical integration. Okay, you can always go to a computer and then do an integration. Okay, so this is in the form of an integral. Now what happens is that so this will be t, and then left hand side is t, right hand side is going to be, I don't know, it will be some function of r. Okay, so it will be some function of r. So maybe I will call it as some phi of r. Okay, so this phi of r is a solution of this integral. Okay, then what you have to do, invert this one, invert this to get r of t. So that is how you get r of t. Now once you get r of t, okay, see, what is your aim? Your aim of the dynamics is to get r of t and theta of t. Okay, theta of t is, these are the two generalized coordinates, right? If you get r of t and theta of t, then you can get x of t, y of t, and everything else is possible. Now, so once r of t is known, okay, so once r of t is known, then you go to this equation, that is your theta dot is equal to L by mu r square, right? So you substitute this here, d theta by dt is equal to L by mu into r square. Now I know r of t, so I will also know r square of t. And now you can do an integration, that is integration from initial theta to final theta, d theta prime is equal to integral 0 to t L divided by mu r square t prime into dt prime. So if you know this, so once r of t is known, then we can integrate the right hand side to get theta of t. Okay, so then the dynamics is solved. So formally, I have said that both r of t and theta of t can be solved by solving these integrals. But then whether you can do it or not in a given problem is a different story. So now at least we know what is the formalism and what are the formal integrals which we need to solve given the potential. Okay, so this is a general discussion. So you can get it, you can get the solution up to this. Okay, yeah. So now there are yeah. So now let us look at so we can, so what do we say? So this is what we call as, maybe starting from this Euler-Lagrange equation for R. Okay, so let us call this as okay, so you have written down these equations and wrote this down. Okay, so now, so from here, okay, so what we are doing from here is trying to solution in terms of quadratures. Okay, so this is general. So that is what I tried to show you, that okay, you can write down a constant of motion. Then from there you can set up these integrals. And if you can solve these integrals, then the problem is solved. Okay. Now, we can do something, some kind of a analysis, because it turns out that we require to get some idea of what kind of what will be the dynamics of this this the system for a given potential. So now let us look at something called some qualitative analysis of nature of orbits. Okay, so what we are going to do this is this analysis is very interesting and also is very important. So now consider let us consider V of r is equal to minus k by r. Then what will be V effective of r? V effective of r is equal to minus k by r. K is positive, of course, plus L square divided by twice mu r square. Okay.
Sir, this L square by 2 mu r square, why it is called a centrifugal potential, sir?
Because if you look at the centrifugal that L square by mu r cube, right? So how did we get that L square by mu r cube? By mr square theta dot, right? So mr square or that force, what we have is L square by mu r cube is like centrifugal force, correct? So that is why it has this kind of a name. Okay, so if there is an angular momentum, there is an outward force, right? There is a force which is attracting towards the center, and there is a force that is pushing it out of the center, and that is usually the centrifugal force.
Okay.
Okay, so now let us try to draw this picture carefully. So let us try to okay, so let us say this is your R. Now I'm going to draw this minus k by r. Okay, so let's say minus k by r will be something like this. Okay, this is minus k by r. This goes to infinity only as r goes to infinity, r goes to 0. So minus k by r. And then I will also draw L square by 2 mu r square. That is a positive term. So you will have something like this. This is L square by twice mu r square. So you can see that. So notice that as r goes to 0, as r goes to 0, L square by twice mu r square goes to plus infinity, okay, faster than minus k by r going to minus infinity. So because of this, what happens? So because of this, so this implies your L square by twice mu r square dominates the sum as r goes to 0. So this is one analysis. Then also note that L square by twice mu r square goes to 0. Okay, so now I am asking, as r goes to infinity, goes to 0 faster than minus k by r going to 0. So what does that mean? This implies minus k by r dominates the sum as r goes to infinity. Now, if you understand these two arguments, then I will be able to draw the sum. Now, the sum of these two, okay, let me draw this. So as r goes to 0, this is what dominates, and as r goes to infinity, this is what dominates. So this is what it looks like. So this is basically your effective potential, the effective of r. Okay. So this is the effective potential corresponding to this. So what I will do is that for a better analysis, let me now try to draw this effective potential alone in this figure. This is r, and then I am going to plot V effective of r. Okay, so this is something like this. Goes like this. Okay, so this is what is going to be the effective potential. Now, so this is 0 of the axis, okay, and this will go to infinity from below. Sorry, this will go to 0 as r goes to infinity from below, and this will go to plus infinity as r goes to infinity because of the arguments that I have made in the previous two arguments. Now, suppose let us try to consider a situation where so let us say I consider case 1 where the energy E is greater than 0. Okay, of course this is true for a given value of L. For a given L, E is greater than 0. Now this E greater than 0, let's say corresponds to some value here. Let's say this is the value of E. Okay, so let us say this is E1. Okay, so this is E1. Now, so if you look at this particular point, so let me call this point as some R1. Okay, so this point is such that so what happens at that point is that the energy will be equal to V effective. So at R is equal to R1, energy is equal to V effective. Okay, now remember we have this half mu R dot square is equal to E minus V effective of R. Okay, so recall that half mu R dot square is equal to E minus V effective of R. Now look at this situation that for R less than R1, for R less than R1, we have, see in this region, R less than R1, your V effective is larger than the energy, because energy is this value, whereas V effective is higher. We have V effective of R is greater than E. That implies E minus V effective of R is less than 0. This implies half mu R dot square is less than 0. That means kinetic energy is negative, which means R dot is imaginary. Okay, R dot is imaginary. And this is unphysical, because this is velocity. Okay, so this is unphysical. What does that mean? That means such a thing will never happen. Such a thing will never happen. That means, so what does that physically mean is that, so there is a force center here. Okay, so this is your force center. And then there is some particular value, I call this as R1 in this particular case, and anything that is coming close to this will not be able to come closer than this. That means it can come from far away. And also notice that for R greater than R1, for all greater than R1, E is greater than V effective of R for all R. And hence there is no such unphysicalness there. That means you can start from any distance and then you can come very close to this, but the distance of closest approach is only R1. Okay, you cannot come closer than R1. So you can see that you can start from somewhere and then come, and then up to this you can come, and then again you go back. Okay, so this is one possibility. Or you are coming from some other direction. So this is one possibility. The other possibility is that you have this force center. Okay, so this is force center, and you are starting from somewhere and then coming and going up like this. And this distance is your R1. So you cannot in any way come closer to this kind of a distance. Okay, this is the kind of orbit that you will have. And for 1 by r potential, one can show that this will be a hyperbola. So these are basically called scattering orbits. Scattering orbits. So this object will come and scatter off from this force center. So these are called scattering objects. Now let's look at another example of let's look at another example where you have this energy to be something like this. Energy is smaller value.
Hello, sir. Your voice is very low, sir.
Hello? Okay. So
Now better, sir.
energy is smaller value, but this time it is negative. Okay. So now you see that there are two values. One is this and one is this. Okay. So maybe I will call this as so I will call this as R2 and R3 if you want. So I will call this as R2 and R3. And notice that for R less than R2 and R greater than R3, in these two cases, R less than R2 and R greater than R3, in these two cases, E is less than V effective, which means it is unphysical. That means you will not have a physical motion in this range at all. So the motion, for this kind of for energy less than 0, okay, like E2 in the figure, is bounded. Okay, so essentially it is something like this. So let's say you have a force center here. There is a particular distance which I called as R2. Okay, and that means there is some kind of a circle whose radius is R2. And then there is another particular distance called R3. Okay, so there is a circle corresponding to that. Okay, and the motion less than R2 is not possible. So this is not possible. And outside it is not possible. Correct? So these are forbidden. It cannot go outside, it cannot come inside. So the motion is always bounded in between. Okay, so these kind of orbits are called bounded orbits or bound orbits. Okay, this is somewhat like bound states that we know in quantum mechanics. These are bound orbits, and the one that I discussed earlier were scattered or unbound orbits. Okay. Now you can see that there is a, so what kind of orbit it is? It is bound, that is, it is between R1 and R2, I know. But is it an orbit that that is actually a closed orbit? That is something which we do not know. Okay, but we can also see there is one closed orbit. Okay, so that is what we will see next. So let us say that we have an orbit like this. We have some energy like this, which is exactly equal to the minimum of this potential. So this is, let's call this as E3. Now what happens at that point? So what happens at that point is that this R3 will become R2, because R2 and R3 are same now. So there is a particular value, so which I may call it as R4. So what will be the trajectory now? The trajectory is just a circular orbit. So let's say you have a force center here, and then there is some radius R4, and then the orbit is a circular orbit. Correct? So this is a circular orbit. So circular orbit is bound and closed orbit. Okay. So now the question is, there is an interesting question that people have asked. So they asked a question, can we say that bound orbits are always closed? The answer is no, we cannot say that. But there is an interesting theorem which is called Bertrand theorem. Okay, so this is called Bertrand theorem. Okay, which says that for two potentials, for V of r is equal to minus k by r, and V of r is equal to half k r square. So this is Kepler problem, and this is isotropic harmonic oscillator problem. For these two potentials, all bound orbits are closed. Okay, for any other potential, it is not clear whether they are closed or not. So for these two potentials, the bound orbits are closed. So this is one theorem. Okay, so I don't know, if we get some time, we will try to look at the proof of this theorem. Otherwise, I would recommend even the latest edition of Goldstein, this proof is removed. But if you go to second edition, so Goldstein, second edition, the proof is there in appendix. Proof in appendix. Okay, it's not very difficult to follow the proof. So those of you who are interested can just look at this proof. Okay, but what is guaranteed is that for every problem, we have this circular orbit. So one of the interesting question to ask is, how stable is this circular orbit? Okay, so one another issue is stability of the circular orbit. So what does it mean? It means we can ask a question. So I have this energy that gives me circular orbit. Suppose if I increase the energy little bit higher. Okay, so that means suppose this is the energy. Now let's say that I increase this energy little bit higher. Will that also be closed? Or how stable is this circular orbit? Okay, that kind of questions one can ask, and they are interesting questions. Okay, now notice that I have done this analysis. Okay, so let us look at, so the analysis, this qualitative analysis, whatever I called. So the analysis of orbits is carried out by considering the potential V of r is equal to minus k by r. Because I have plotted this function, V of r is equal to minus k by r. But classification of orbits, okay, classification of orbits argued here is more general and applicable to any potential that goes to 0 as r goes to infinity slower than 1 by r square and goes to minus infinity slower than 1 by r square as r goes to 0. So any potential that exhibits this particular behavior is basically, this classification is valid. However, okay, so this is one point. Okay, however, the method of analysis is valid even for potentials that do not satisfy kind of 1 and 2 that I have written earlier above. Only this classification of orbits will not be true, but you have to have another classification, but this method will still work. For example, let's say that you have a potential which is so let us say you have a potential which is equal to minus k divided by r cube, something like this, r cube. Okay, so that means what? This goes to infinity faster and it goes to 0 also faster. So that means, so this means what? This means as r goes to 0, minus k by r cube dominates, and as r goes to infinity, L square by twice mu r square dominates. So it is basically the reverse of the previous case. So you can still do this. For example, you can plot this. So let's say this is your minus k by r cube. and this is your L square by twice mu r square. Now, since this is potential is going to dominate, your effective potential will be something like this. So it will start like this, and then go like this, and then go like this. So this is going to be your effective potential. Now, of course, you try to talk about different energies and find out what happens. The classification will be different, but the methodology, whatever we have used, still works even for these kind of potentials. Okay, so this is the advantage of using what is called the effective potential, and then the constant of motion. Okay, so this is one very important analysis where you can get qualitatively what kind of orbits are there, and for which orbits are bounded, which orbits are unbound, what should be the energy for this. Now, let me make some remark about the initial conditions. Remark on initial conditions. To solve the problem, we have to give some initial conditions, right? Okay. Now, if you think that we have two generalized coordinates, r and theta are generalized coordinates. So you have to give r at 0, theta at 0, r dot at 0, theta dot at 0. So these are four sets of initial conditions that we may have to give. Okay, so initial conditions. But we can also think of this dynamics in the following way. Suppose if you give two constants of motion, that means energy E is a constant of motion and L is a constant of motion. So you give E and L, then you give only two initial conditions like r at 0 and theta at 0. Okay, this is equivalent. Okay, so this is equivalent. How do we see this is equivalent? Because you know that L is equal to m r square theta dot, right? So if r of 0 and theta dot of 0 is given, we get L is equal to m r square at 0 and theta dot at 0. And once we get L, and L is not going to change from time to time. So we can, so once you know r of 0 and theta dot of 0, you can calculate L. Similarly, you know this E is equal to minus, E is equal to half mu r dot square plus V effective of r. So if r of 0 and r dot of 0 are given, that is if r of 0 and r dot of 0 are given, we get E, which is equal to half mu r dot square of 0 plus V effective of r of 0. That means if you are given this, then you can get E. Once you get E, then E is going to be constant of motion. E is not going to change. Okay, so giving r0, theta 0, r dot 0, theta dot 0 is equivalent to giving E, L, r0, theta 0. And since E and L are not going to change, we can ask, we can try to classify orbits for different values of E, different values of L, like that. So in the previous analysis, we have chosen different values of E. It is equivalent to choosing different initial conditions. So we actually try to analyze what are the possible trajectories for minus k by r potential. But later I also made a comment that this minus k by r potential can be generalized. You can have any potential which registers a kind of a slower going to infinity at 0 and slower going to infinity at slower going to 0 at infinity. So that is the remark that I made here. Goes to 0 as r goes to infinity slower than 1 by r square, and goes to minus infinity slower than 1 by r square as r goes to 0. So this so you can have any potential which satisfies this condition. This analysis of having unbound orbits and bound orbits and circular orbit, this analysis will go through. And if you have a potential which does not satisfy these two conditions, then you have to, of course, draw the diagram and then do the analysis separately. But this method still will work to get information about the classification of different types of orbits. Okay. So I will stop here. If you have a question, you can ask.
Sir, this you wrote this E as half mu r dot square plus B effective of R naught. Sir, can we take that to be the Hamiltonian?
Yes, you can take that to be Hamiltonian. Yes.
Sir, but usually when we write Hamiltonian, we write it as kinetic energy plus potential energy, no sir. But here the potential is effective potential, no sir.
Yeah. So basically, that centrifugal term that is there, that will come out as a rotational kinetic energy. So there is a radial kinetic energy and a rotational kinetic energy, and then the potential.
Okay, sir. Sir, and this Lagrangian always is T minus V, or is there any case where the Lagrangian is not equal to T minus V, sir?
See, Lagrangian can be slightly, it can be more general form. For example, when you go to especially field theory, etc., this T minus V kind of a form need not be preserved. But for all this particle dynamics, I think you can assume safely that it is T minus V. And of course, if there is some velocity dependent potentials, then you have to appropriately consider them with a velocity dependent potential, which we will see when we do charged particle in electromagnetic field.
Yes, sir. Okay, sir. Sir, and I have another question, sir. Now, this Kepler's law you had, it is for all the planets he told, no, sir. So it's not a two-body problem. So the analysis that we were doing today was only for a two-body problem. We have made it into a one-body problem, and for that only we have done the analysis, no, sir.
Correct.
So my question is that all of the planets will be orbiting in the same plane, sir, in our solar system. Is it like that, sir?
No, not necessarily.
Okay,
See, a given orbit. See, the point is something like this. If you consider the orbit of the Earth, we are going to consider Earth and Sun as a two-body problem. If you are considering orbit of Mars, then you are going to consider Mars and Sun as a two-body problem. If you consider Jupiter and Sun as a two-body problem. So you can find out by considering these two-body problems in this way as what is called the plane. You can fix the plane. But then it is not strictly a two-body problem because there is a gravitational interaction
due to other planets.
So there will be some what is called the perturbation will be there, and that will
Yes, sir.
alter this planes slowly. So there is something called, in fact, there was something called, that precession of the
Mercury's
Mercury.
orbit.
Yeah. So those things
Yes, sir.
will happen because of this. But when we actually try to solve this problem in this dynamics, we are ignoring all those things. In fact, if you consider three-body problem, it has been shown by people that it is not even integrable.
Oh, okay, sir.
Yeah. So many body
Okay, sir.
problems are always solved by considering them as interactions, as pairwise interactions always.
Yes, yes, sir. Okay, sir.
Mm.
Thank you, sir.
Ah.
Hello, sir.
Yeah.
Sir, invariance denotes symmetry. Okay, sir. Oh, yes, no, sir.
Hmm.
Hello.
Yes. Go ahead.
Invariance denotes symmetry.
Hmm.
Am I right?
Yes.
And you said that a cyclic coordinate can be considered as invariance of the system.
Hmm.
Like can be is present because of invariance of system.
Hmm.
But not invariance does not imply there is a cyclic coordinate.
So what I'm saying is that you can have a general Lagrangian structure even if the coordinate is not cyclic. There can be invariance. So invariance is a more general property, and if something is cyclic, then it is invariance is trivially it is there, because suppose if Lagrangian doesn't depend on theta, now I change theta to theta plus some theta prime, then also Lagrangian will be same, right? So the invariance is is a trivial property if the coordinate is cyclic. But if the coordinate is present and then also there is an invariance, that is also possible. That is why I am saying cyclic means there is invariance, but invariance does not mean that the coordinate is going to be cyclic always. Even though the coordinate is present in the Lagrangian, we can have invariance. But if it is not present, definitely there is an invariance of any change or transformation to that coordinate.
So here cyclic coordinate means conserved quantity, no, sir.
Cyclic coordinate means the corresponding momentum, corresponding canonical momentum is conserved quantity.
Okay, sir.
That coordinate is not conserved, but the corresponding canonical momentum, which is dou L by dou theta dot, no, that is conserved.
Okay, sir. So, but for Noether's theorem, for every symmetry, there should be a conserved quantity, no, sir.
Yes, that is.
So, but you're saying for invariance,
So what I'm saying, that's what I'm saying is, if there is a cyclic coordinate, their corresponding canonical momentum is a conserved quantity. Suppose if there is an invariance, okay, then also there is a conserved quantity, but then that you have to construct. It is not just the momentum alone. You have to construct a conserved quantity. Its existence is guaranteed by Noether's theorem, but then you have to construct that quantity. It is not just the momentum that is conserved. But if it is cyclic, then it is very easy to identify conserved quantity. No need to construct. You just have to take the corresponding canonical momentum, and that is conserved. So in some sense, the existence of a cyclic coordinate is a very stronger form of invariance. That's what I can say.
Okay, sir.
Okay. And if there are no questions, then we can close.
Yeah, dear students, we are about to close the session. Do you have any more questions? Or shall we close?
Yeah,
I think silence means I can close.
Yeah.
Oh, thank you, Professor. Today,
Thank you.
I am also very happy. Many students started talking today. So I'm really happy in that sense.
Yeah.
Thank you,
Okay.
Professor. Good night.
Good night.
Thank you, sir.
Good night.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir.
Thank you.
So I am closing.
Yeah,
Professor.
yeah.